Understanding volcanoes. Volcanoes are vents in the Earth's crust that allow molten rock, gases, and ash to escape from deep underground. They sit above weak points in the crust where heat from the planet's mantle rises toward the surface. At the heart of every volcano lies magma, molten rock that collects in underground chambers. When the pressure in these chambers builds beyond what the surrounding rock can hold, the magma forces its way upward. The way it escapes, quietly or violently, depends on several key factors, which we'll explore step by step. Magma composition. The first and most important factor that determines how explosive a volcanic eruption will be is the composition of the magma itself. Magma is made primarily of molten rock, but it also contains dissolved gases and minerals. Not all magma is the same. Some types are thin and runny, while others are thick and sticky. Basaltic magma, found in places like Hawaii, is fluid and low in silica. It allows gases to escape easily, so eruptions tend to be gentle, with flowing lava fountains. Rhyolitic and andesitic magma, common in subduction zone volcanoes such as Mount St. Helens or Krakatoa, is rich in silica. Silica makes magma much more viscous, or sticky. Thick magma traps gas inside, increasing pressure until it explodes. In short, high silica magma acts like a thick lid over a pot of boiling water, while low silica magma behaves more like soup simmering gently. Gas content gases are the real drivers of volcanic explosions. Magma deep underground contains water vapor, carbon dioxide, sulfur dioxide, and other gases dissolved under immense pressure. As magma rises toward the surface, the pressure decreases, like opening a soda bottle. The dissolved gases suddenly form bubbles and expand rapidly. If the magma is thick, these gases can't escape easily. The trapped bubbles keep expanding until they shatter the surrounding rock and blast magma into the air as ash, pumice, and volcanic bombs. Volcanoes with gas-rich, viscous magma can release energy equivalent to many nuclear weapons in a single eruption. Pressure buildup. The underground magma chamber behaves like a giant pressure cooker. Over time, fresh magma pushes into the chamber from below, adding both heat and gas. The surrounding rock holds it in place like a cork in a bottle. If magma finds cracks or faults, it can move upward. But if it's trapped by strong rock or thick plugs of older lava, pressure continues to build. When that cork finally fails, all the compressed gas and magma escape in a catastrophic release, producing the explosive eruptions we associate with stratovolcanoes like Mount Pinatubo or Mount Vesuvius. Water's role. Water often plays a surprising part in making eruptions more violent. Many volcanoes are found near coastlines or beneath glaciers. When magma comes into contact with underground water or ice, it flashes that water into steam almost instantly. Steam expands much more rapidly than liquid water, which can turn a relatively ordinary eruption into an explosive phreatomagmatic event. This is one reason volcanoes on oceanic islands like Krakatoa in 1883 or Hunga Tonga Hunga Ha'apai in 2022 can erupt with exceptional force. The interaction between magma and seawater amplifies the blast and sends huge columns of ash and gas into the atmosphere. Volcano type. Not all volcanoes erupt in the same way. Shield volcanoes like Mauna Loa in Hawaii have wide, gentle slopes and basaltic magma. They tend to have frequent but mild eruptions, mostly lava flows. Stratovolcanoes such as Mount Fuji, Mount St. Helens, and Pinatubo have steep sides and are built of alternating layers of lava and ash. They typically erupt with much more explosive power because they often have viscous magma and trapped gases. Caldera volcanoes, like Yellowstone or Toba, are among the most explosive. When their massive magma chambers empty in an eruption, the ground above collapses, creating vast depressions and releasing huge volumes of ash. The structure of the volcano, combined with the magma's chemistry, determines whether an eruption is a gentle lava flow or a devastating blast. Plate tectonics. To understand why some areas produce especially explosive volcanoes, we need to look at plate tectonics, the slow movement of Earth's crustal plates. Explosive volcanoes usually form at subduction zones. where one tectonic plate slides beneath another. The descending plate carries water and sediments deep into the mantle, lowering the melting point of the rock and creating gas-rich, silica-heavy magma. In contrast, the volcanoes that form at hotspots, like Hawaii, or at divergent boundaries, like Iceland, tend to have less explosive eruptions because the magma is hotter and less viscous. Famous explosive eruptions history is full of examples that show just how destructive explosive eruptions can be. Mount Vesuvius in AD 79 buried Pompeii and Herculaneum under meters of ash and pumice. Krakatoa in 1883 produced one of the loudest sounds ever recorded, generated tsunamis, and changed global temperatures. Mount St. Helens in 1980 blasted away the top of the mountain and released energy comparable to several atomic bombs. Pinatubo in 1991 sent ash and sulfur dioxide so high into the stratosphere that it cooled Earth's climate for several years. All these eruptions shared common factors: viscous, silica-rich magma, abundant gas, and, in many cases, interaction with water. Ash columns and pyroclastic flows. One hallmark of explosive eruptions is the towering eruption column of ash and gas that can reach 20, 30, or even 40 kilometers into the atmosphere. If the rising column becomes too heavy to stay aloft, it collapses under its own weight, sending scorching hot clouds of ash, gas, and rock fragments rushing down the volcano slopes. These pyroclastic flows can move faster than 100 kilometers per hour and reach temperatures above 500 degrees Celsius. They are among the deadliest volcanic hazards, capable of flattening everything in their path within minutes. Volcanic Explosivity Index, VEI. Scientists use the Volcanic Explosivity Index to rank eruptions by their power. The scale runs from 0 to 8. A VEI 0 eruption is a gentle lava flow, like those often seen in Hawaii. A VEI 5 or 6 eruption, such as Mount St. Helens or Pinatubo, can darken skies over an entire continent. A VEI 7 or 8 super eruption, like Toba 74,000 years ago, can release thousands of cubic kilometers of material and potentially affect global climate for decades. The VEI helps scientists and emergency managers communicate the likely hazards and scale of an eruption to the public. Monitoring and early warning. Modern volcanology has made great strides in monitoring the warning signs of explosive eruptions. Instruments measure ground deformation, gas emissions, earthquakes, and even changes in local gravity. By tracking how magma is moving and how gases are escaping, scientists can often give communities days or even weeks of warning before a major eruption. While we can't prevent eruptions, early evacuation and disaster planning save lives. Why explosiveness matters. Understanding why eruptions vary in explosiveness isn't just academic. Explosive eruptions pose enormous risks to communities, aviation, agriculture, and global climate. Ash clouds can ground aircraft, damage engines, and blanket entire regions. Sulfur aerosols from massive eruptions can temporarily cool Earth's surface, disrupting weather patterns and harvests. By studying the chemistry of magma, the role of gases, and the geological setting, scientists can better predict which volcanoes are most likely to erupt explosively and prepare accordingly. Closing perspective. Explosive volcanic eruptions result from a combination of gas-rich, silica-heavy magma, rising pressure in underground chambers, and often the presence of water or ice that amplifies the blast. The same natural forces that build our planet's landscapes can also unleash some of its most destructive events. Through continued research and monitoring, humanity is learning not only to understand these forces, but also to live more safely alongside them.